Good morning to everyone. I'm Margherita Ciccaglione and I'm a PhD student from University of Naples Federico II. I'm going to talk about the use of one-line models and littoral drift rose concept in predicting long-term evolution of the Molise coast. Let me start by giving you some background information. You know, the analysis and prediction of shoreline changes are challenges that scientists have recurrently to face, especially when structural or non-structural protection measures already exist or are to be planned. These kind of problems are usually addressed via two types of analysis: short-term, that conceal with cross-shore dynamics, such as storm events, and long-term, related to the long-shore dynamics, as the littoral transport. The main purpose of this study is to focus on the long term. We want to understand how reliable long-term forecasting tools are in the description of the shoreline evolution. Practical coastal engineering faces with this kind of investigation through the so-called equivalent wave concept, assuming that shoreline changes may be significantly correlated to a single component of wave climate. So we wonder if this equivalent component is efficient in doing so. But let's have a look on what we are talking about. As the analysis timescale increases, cross-shore cyclical movement of the shore can be neglected, as commonly assumed, and the dynamics related to the directional persistence of wave climate, namely the littoral drift, are considered to be the only responsible of the shoreline planform evolution in the long run. Dealing with such large timescales, which range between 10 and 60 years, in most cases numerical models are the only tools to be used, among which the one-line models. It is known that one-line models like Genesis integrate the one-line equation, that is, the mathematical tool that returns the rate of shoreline change due to the littoral drift gradient. The model output is related to a number of factors, particularly the wave climate, which represent a leading input to the model. However, it is often reduced to a single sea state equivalent to the whole climate, which is somehow supposed to rule the entire shoreline evolution. Although well accepted and employed in applied coastal engineering, it is noteworthy that scientists do not agree on the equivalent wave existence, as Sylvester wrote in 1984. Anyhow, even assuming such an equivalent wave exists, no universally accepted estimation procedure has been proposed so far, and no one has been trying to clarify to what extent the equivalent wave approach is reliable. For these reasons, two issues deserve to be investigated. One is the most convenient way to select the climate equivalent sea state. The other is assessing at which extent the equivalent wave could explain the long-term evolution of shorelines when used to force a one-line contour model. So let's try to go in deep with these issues, and let's talk about the littoral drift rose concepts that seems to provide a quick and easy engineering way for representing the wave climate. The concept of LDR was first developed by Walton and Dean. It is a compact polar graph representation of littoral drift potential for various smooth shoreline orientation. For a given deep water wave climate characterized by a series of events, the potential littoral drift rate is a function of sediment characteristics, wave characteristics, and shoreline orientation. As shown in the figure, positive and negative lobes can be distinguished, and moreover, the graph shows a null point, that is, the shoreline orientation at which no sediment transport is seen. In improving their studies, Walton and Dean in 2010 provided an accurate discussion, where the applicability of LDR was investigated in depth. The others, in fact, showed that in many practical applications, the LDR based on the whole climate was well approximated by that of a single equivalent wave component, with significant wave height, wave period, and deep water direction. According to Walton and Dean, the equivalent direction corresponds to the null point of the LDR. Wave height is fixed through circular regression to have the same littoral transport magnitude, while for the equivalent period, no clear specifications are given. In addition, for locations of null points with zero net flux, they present two different types of climates, stable and unstable. Stable LDRs occur in climates where a dominant wave direction exists, which is nearly perpendicular to the mean shoreline trend. In this case, the coast reacts to any natural or man-made perturbations by smoothing them out. In the less frequent case, where longer fetches exist more parallel to the shore, an unstable LDR results. In this case, a bimodal wave climate is seen. On the right is pictured this case where the climate consists of two wave components parallel to the coast. Under this condition, any natural or man-made perturbations tend continuing to grow, so cusps will accrete and holes erode. Walton and Dean said that the unstable LDR is the case of the elongated bay or lagoon, in which a climate bimodality is commonly observed, and the applicability of the equivalent wave concept seems to be limited. So we tried to focus on these uncertainties, and particularly at which extent the LDR equivalent direction is capable of explaining the main features of the shoreline trends, even in a bimodal climate. Which period to be associated to the equivalent wave, if the peak period or the tail of the probability distribution, and if a monthly representation of LDR equivalent wave could be more successful than the annual one. So to focus on these uncertainties, we examine the case of Molise coast, located in southeast of Italy, fronting the Adriatic Sea. The Adriatic Sea has a geographical conformation similar to the elongated lagoon studied by Walton and Dean. Because of this, it is in fact inherently subject to a strong bimodal wave climate, so making it the best case study for analyzing the limitation of the equivalent wave approach. As we can see from the picture, two modes can be easily distinguished into the Molise wave climate, one from east sector, the other from the northwest sector. In the upper right figure, it is also pictured the seasonal behavior of these directional modes. East mode dominates during winter, while the northwest one during summer. In addition, a shoreline change analysis has been carried out by comparing the Molise coastline position in 2004, 2011, 2014 and 2016. Data comes from the digitalization of photograph reliefs from different sources, performed in collaboration with the University of Molise. The linear regression rate, LRR, has been used as the indicator of the rate of the shoreline change. From the LRR function of the 36-kilometer-long coast of Molise, we selected the significant erosion accretion areas, as we can see from the lower right picture. There are 4 erosion areas and 5 accretion areas. Now, in this slide, the figure on top shows the 2004-2016 LRR function with the selected erosion accretion hotspots and the structure systems covering the coast, whereas the lower figure displays the location of the erosion accretion areas. From the inspection of the two, it can be seen that the foremost erosion areas, A1 and E3, are located south to the Trigno and Biferno rivers. In both cases, the retreat has occurred just southward a growing field. Moreover, the area next to the Santa Cristina harbor has accreted northward and eroded southward. So, similarly to what observed for the previous areas, the erosion zone is located south to a growing breakwater system. Finally, the area just north of the Saccione stream jetty, A5, has accreted because of an updrift effect. So, these results seem to suggest that a net northwest to southeast littoral drift exists. Therefore, a directional persistence of wave climate exists. As regarding the area A2, A1 and E2, their origin is not readily explained, but we will demonstrate that they are an effect of the existence of an equivalent direction of the wave climate. To have a deeper insight, a dominant direction of waves has to be considered, and a simple modeling genesis has to be created. Because of the time, I will focus on the area A2, but the same investigations and results have been obtained also for A1 and E2. Now, to run Genesis, we adopted a single wave component of 10 degrees north, and I will explain why. First of all, assessing the Molise LDR, we see that a null point is placed at the shoreline orientation of about 10 degrees north. That is consequently, according to Walton and Dean, the equivalent wave direction. This direction seems to be supported by the shoreline orientation of accretion area A5. A5, in fact, can freely adjust to the sea, and as shown has a nearly constant orientation, which is close to 10 degrees north. Hence, the latter can be assumed as the offshore equivalent wave direction. Therefore, the Genesis model has been set up for the area A2, modeling in a simplified manner the breakwater system, and the equivalent wave has been run for 50 years to attain a stable shape in plan form. In general, simulation results correlate quite well to the observed shoreline trend. Anyway, to check the sensitivity of a solution, the equivalent wave angle has been shifted by 10 degrees north, either to the north or to the south, but this direction do not capture the shoreline trend, as we can see from the figures. So the LDR equivalent wave seems to be the only one capable of explaining the shoreline evolution. Now, we found that an equivalent wave component exists, but how effective is this direction? So we further investigate the explanatory power of this equivalent wave direction. So we focused on the area just south of Trigno river mouth, which corresponds to the E1 erosion spot. The shoreline extends for 5.2 kilometers and is protected in the northern part by a field of 12 groins. The Genesis model has been set up, as shown in the right figure, and we compare the Genesis output with the measured LRR of the E1 erosion area. To evaluate the model performances, two prediction indexes have been used, the correlation index and the relative mean square error. Numerical simulations have been run by varying groins permeability, transport coefficient, equivalent wave period, and the annual or monthly representation of the equivalent wave. We made more than hundreds of analyses, and they revealed that the proper use of such parameters can raise the determination index up to 90%, which is surprising given the simplified model and assumptions. The perfect fit can be obtained with the annual LDR equivalent component of 9 degrees north with the longer period associated. Here we obtained the maximum correlation and the minimum error. Lower figure shows the comparison between the measured and predicted LRR in this best condition. As we can see, the fitting is incredibly similar. In conclusion, let me sum up my main points. First of all, from analysis, we see that the use of the equivalent wave as a stationary forcing may lead to a reasonable prediction of the shoreline response. Moreover, the use of the LDR equivalent wave may be totally appropriate even in a bimodal climates. In addition, the longer period seems to be the best one to be associated with the equivalent wave. And finally, numerical experiments reveal that the monthly representation of the equivalent wave seems to be not so powerful as the annual one.